So we'll talk about the internal ISWAT challenge and discuss the motivation for this challenge and talk about what we considered when we were formulating this challenge or guidelines for this challenge. So in general, challenges are really useful and important things. They help us understand when and under which conditions different codes may operate better. They also may help us identify missing physical processes or where we could improve boundary conditions or parameterizations in the codes. So first of all, I think the main challenge, usually challenges from my experience, is that people are busy and they are not specifically funded to work on this challenge. So it's often difficult to get people to participate in the challenge. And that's one of the greatest challenges. But of course, we want to have a number of different codes with different physical processes, different boundary conditions, different models of waves, and so on and so forth. The next challenge is probably in setting up a challenge like that is in setting up the code so that they have similar conditions and similar setup. That includes, because some of the codes use different boundary conditions. They could be set up at different radial distances. They can use different types of data. So comparing the codes that are set up differently, different locations with different amount of data, with different amount of knowledge about the current state of the system is certainly very difficult or almost impossible. Another challenge is that to objectively validate the codes, they need to be run for a relatively long time. If they are run for a short time, then it's not clear how much the results of the code are affected by the initial condition that is often taken from observations. And the last challenge is that the codes need to be, ideally the codes need to be run by a third party that can evaluate the code so that there is no turning knobs or adjusting parameters and so on and so forth. So these are main challenges. And also they need to be validated in a similar systematic way so that there is no difference between you don't choose type of validation or favorite metrics where one code maybe runs better than the other. So it's really important to have a third party evaluating the code that wasn't involved in running the code or developing. So for the first challenge, considering all these things, we're thinking about modeling the entire year of 2017. Some of the codes will not be able to run for so long time because they require much more effort. So this should be considered, of course, only as a guideline. We will also provide selected events that people who cannot run the entire year 2017, then they would be still able to participate in the challenge and we would be able to compare with them and compare the results. So what we propose is to perform simulations for entire year 2017, for which we have Van Allen probes and it's relatively active times. But because we'll be validating by Van Allen probes, the idea is that the codes are allowed to use geosynchronous data, but will not be allowed to use Van Allen probes data for boundary conditions or for any other input. So it may be a challenge for some of the codes who, let's say, set up boundary conditions from Van Allen probes for lower energy boundary of the code or for inner boundary condition. So we would discourage that because then it would be difficult to judge if that's the results of the code or the results of the simulations really, or the results of the boundary condition that somehow is used by the code. In general, we would discourage any use of Van Allen probes data because some of the codes may be also using that for diffusion coefficients or for data on waves and so on, so that it's quite clear that that the model performed the simulation without being affected with the end result that we're validating. So here's more specifics on the challenge. So modelers will be we suggest that modelers do use only solar wind conditions and geosynchronous ghost data. We also would like to ask modelers to include more documentation on the results, so that CCMC can understand what is there, and then later we could also understand what was done by the modelers. So brief description of the code, including references, description of input data for simulation, so that we can also see what's the inputs and how they change the simulations. And also, if the challenge guidelines cannot be satisfied, then a list of exceptions, let's say used for null probes, data for the inner boundary conditions or for the outer boundary conditions, and so on. So simple ASCII codes would be ideal, and at least for this initial round, we are suggesting 0.9 MeV and 1.8 MeV energies, sort of relativistic, and a little bit higher energy. It's also mega-ice and wrapped energies. There is ongoing intercalibration of this instruments and adjustments of that, and that could be always adjusted in the future if we find that some slightly different energies are better. But for now, we're selecting 0.9 MeV and 1.8 MeV. Simulations should be done for 2017. If not, then we're selected here a couple of intervals in 2017 that people can run. So we plan to extend this challenge in the future, and we plan to have data simulative challenge, so codes that can use data, and then we can use GPS data and pulse data and so on. And in this challenge that we're planning for the future, then people could use any type of data, also except for Van Allen probes data. And the third challenge that we were considering also for the future is a prediction challenge. In this challenge, you can use any type of data in the past, but predict the future. And of course, in the future, there is no really data given or provided. And so that would be also an objective and also very interesting challenge that will show how well we can predict the radiation belt flux. So altogether, we'll have 3 challenges: one for the codes, one for how well we can reconstruct the environment with data simulative codes, and how well we can predict the future. I'll stop on that. Thank you.